What's up, guys? I'm Force. My name is Mass. I'm Acceleration. And together we're Force equals Mass times Acceleration.
What we're going to do here is we're going to identify the coordinate system. We're going to identify it as theta x and theta y. Now we're going to do that along this plane. So theta x is going to be along the plane and y is going to be normal to it. So this first equation, which identifies the mass moment of inertia, angular velocity, and the moments acting about the center. Now we're going to identify those moments acting about the center by looking at the free body diagram, and we see that gravity and normal force go right through the center. And the only moment acting on the object is this unknown friction force. Then we're going to integrate this due to our assumption that at rest, initial velocity and angular velocity equal to 0, we can just totally get rid of this altogether. And so that leaves us with these two equations as follows. Now, when we integrate this, this just turns into our moment multiplied by the change in time, which is right here in the interval, and that is equal to our final value. So then we look right here, and we know that this right here, this angular velocity, is equal to translational velocity divided by r. And that shows up in this equation right here with the substitution. Now we just want to isolate the moments on this side, or we just want to isolate the force times time on this side, and so we're going to move this radius over here. The force of friction multiplied by the change in time is equal to the mass moment of inertia multiplied by the final velocity divided by radius squared. And for now, that's where we'll stop with this equation. We're about to move to the equation with force. So second part here, we're going to be looking at this equation. We know that V1 equals 0, and that what we're left with is the integration of the forces equals mv final. So we have the forces here, mg sine theta, which acts along the plane, subtracted by the frictional force times delta t. We distribute the delta t, and we notice that this is from previous part of the equation. We can substitute that for that force of friction times delta t. So when we do that, we get mg sine theta delta t minus IVF over r squared equals mass times velocity final. We isolate this mg sine theta times t, or times delta t, and we factor out that velocity final.
We're going to divide this side of the equation by everything in here, which is presented here. Now we have an equation for velocity final. Now we're going to go and determine the velocity for both the ring and the disk using the inertias provided. The inertia
Ring
is 1/2 mr squared, and the disk is 1/2 mr squared. So we plug them in separately, and we plug in the inertia for both objects. After simplification, the radiuses cancel out for both, and we are left with, on the left-hand side for the ring, our velocity final is, we have 2m in the denominator, which further simplifies to just have g sine theta over 2 times delta t. On the other hand, we have disk, and likewise, the masses cancel out, and we have g sine theta delta t all over 3/2. Now, if we go over here, we have to find the ratio of these velocities. Now, we already have the velocities of the disk and the ring, so all we have to do is divide them by each other. Now, but the problem asks us both to find velocity and the omega. Now, these both are equivalent to each other. Since omega are the same, omega's velocity is equal to omega times the radius. Multiplying by the radius would just end up canceling out anyway, so the ratios are, in fact, the same. So then we just plug in the velocities that we acquired previously into the format here, and everything cancels out. The gravity cancels out, sine cancels out, and time as well cancels out. And after much rearranging, we end up that the velocity of the ring ratio with velocity of the ring relative to the disk is 3/4.
So we're looking for the distance between these, both the disk and the ring, down after 10 seconds. So we're going to use the simple kinematic equation. So we know this is 0, it was at rest. So we're going to use that, d equals 1/2 at squared, and find the distance traveled. So for the ring, simply 1/2 g sine theta is going to be our acceleration, and we're just going to leave t as is, multiply that by 1/2, and we get 1/4 g sine theta times t squared for that. For the disk, similarly, 1/2 multiplied by this is the acceleration, 2/3 g sine theta, multiplied by t squared, we have that this is 1/3 g sine theta times t squared. So we notice that 1/3 is larger than 1/4, so this will be in front, the disk. And so, proceeding, we will see that this distance between them is just the absolute value between their distances. So we have similar terms here with the g sine theta times t squared. So we just factor out these 1/3 minus 1/4, and we get 1/12 times g sine theta multiplied by 100 equals our delta t.
We found that the ratio of the velocities is equal to the ratio of the angular velocities, which equal 3/4. Now the change in distance after being released simultaneously after 10 seconds, we found it was 1/12 g sine theta times 100.
Yeah!
We did it! Rich, high five!